So hello everyone, welcome to week 6 of problem solving session. So I'm Mochandra Paul and I am a PhD scholar at the Department of Chemical Engineering at IIT Kanpur, and I have been for the past 5 weeks. So I've been helping you guys out for the problem solving sessions, like help you solve some assignment problems. So those of you who are all coming for the first time today, welcome. So I am actually working in the field of tissue engineering for my PhD thesis. And like I have had experiences with various kind of biomaterials, and using those biomaterials, I have tried to make various kind of scaffolds again for tissue engineering application. And if you guys have any queries during the session, feel free to ask. If outside the session, like after you guys leave, if you have additional queries, feel free to post in the discussion forum. And like this, we'll be meeting every Saturday from 4 to 6 p.m. till the end of this course. And the recordings of these sessions are available in my YouTube channel, and the notes are also provided to you. You guys can freely go through it, and like it will definitely help you with your queries. The interface that you guys have joined in for the meeting, it doesn't have the chat option. So if you guys have any queries, feel free to unmute yourself and ask, or you can raise your hand as well, so that maybe I can call upon you, and you can then ask. So any way is fine with me. So let's begin. So I'll be starting with the small introduction about metallic biomaterials. So in today's class, I'll majorly focus on the metallic biomaterials. Next week, I'll give more stress on the polymers. So, what are metallic biomaterials? Those are metals basically, and they are biocompatible. That is why they are used for biological applications. Like when they are come in contact with biological system, it has shown non-toxicity or good properties. Okay, it has not harmed the host. That is why they are used like as a biomaterial for biomedical applications. They are explored for various application areas like bone and joint replacement, dental implants, cardiovascular devices. So under cardiovascular devices which directly come in contact with the blood, right? So these include the pacemakers, heart valve, stents, then various kind of processes which are like attached to the patients externally, not internally. Those are also made up of metals, and the surgical tools that are used during the surgery, those are also made up of metals. And the material should be such that the material used to make these tools or whatever implants are biocompatible. It doesn't harm the host. So some advantages are there and disadvantages. Advantages include like it can handle a large amount of load. That is why it has a load bearing property. Then it can be easily fabricated. So we have been working with metals individually for thousands of years. So the technology that exists to process metals have very well developed. So we can use metal to create any type of shape we want for our application. It has a very good fracture resistance. Means once the fracture means it mean it well, after a very long cycle of stress and strain, or after a very long period of usage, fracture develops. All right, it doesn't fracture quite easily, in other words, and it can be transformed into any shape and size. So it like can be made into metals, sorry, wires, then sheets, or any irregular shape you can make it into. Then disadvantages are there also. So metals, they have comparatively very high elastic modulus. So it shows a disadvantage of stress shielding. Uh, it becomes critical in orthodontic applications where you are using a metal implant to replace a fractured bone. Okay, so in that case, although you have used the metal implant to support the growth of the bone, but over a period of time, what people have observed that the bone doesn't grow well because the load on the bone is less. Most of the load comes on the metal implant. So that in turn hampers the regeneration of the bone itself. So the formed after healing, after a period of say 6 months, 1 year, whatever period of time of healing is there, the reconstructed bone or the regenerated bone is not of good quality. So that happens because of mismatch of strength between the bone and the metal implant. That is stress shielding. Then there is another disadvantage. It is corrosion resistance is very poor. So when the metal implant comes in contact with our body fluids, be it saliva or blood, urine, or whatever body fluid or enzymes and proteins are there, so they contains various kind of hydrolases enzymes, or the water content is very high. So all these factors and the flow, continuous flow is there over the metal or surrounding the metal implant, that can cause surface corrosion. Like over a period of time, the iron starts like corroding out, okay, from the surface of the metal and comes into our blood or whatever fluid is there. Then it in turn it can cause some inflammatory response as well. So in that case becomes worse. We don't want that case. So people have then tried to modify these metallic biomaterials to prevent this kind of scenarios. Metal by itself, it will corrode eventually when it is inside the body. Now, various examples are stainless steel, specifically stainless steel of low carbon grade 316. So this grade of stainless steel is used for biomaterials. But when you use stainless steel katori or thala, like whatever utensils that are used in home, that is of 304 grade. Okay, so that grade and the grade that is used for making implants is different. It is 316, low carbon 316 grade. And also there are alloys like cobalt, chromium, molybdenum alloys, then titanium alloys, even pure titanium is also used. And these 4 5 examples are most commonly used for orthodontic applications, okay, for bone, cartilage, these kind of applications. Whereas tantalum is comparatively like soft material, so it can be it has been used for dental application as well. Then what are the physical and the chemical properties of metals? Quickly, we will go through. So it has a luster, means it shines very nicely. So, and then it is electrically and thermally conductive. It has a very high density. The melting point of metals are very high, means you need big furnaces that can go up to thousands or even more temperature to melt the metal into liquid, and then you can process it. So that for that you need special fabrication facilities. Then metals when heated it can be formed into wires and sheets. So ductility is like tendency to turn into thin wires. Malleability means it can be converted into sheets. Then there are various chemical properties as well. So metal surfaces are highly reactive. So if you remember during our last session, I told you how the metallic bonds are there in metals, where there is a core of a cation and surrounding it there are electrons. And these electrons basically acts as glue to hold the surrounding cation. Now, these electrons, they can freely move. They are not covalently bound like it is seen in polymers. So when some reagent or any body fluid starts to corrode, then the surface becomes, or the electrons on the surface becomes much more active, and they participate in various kind of reactions, which is why you see various metals, even stainless steel, can have rusting. So rusting, the phenomena of rusting happens because metals have highly reactive surfaces. Okay, then it corrodes easily, as I explained you already. So in presence of any harsh environment, the surface or the ions from the surface, it will start leaching out from the surface. That is corrosion. Now, I hope you have understood, like it is a very basic thing, what you have already seen in the lecture. The previous slide, it was very basic. I hope you have understood. Now, let's come to this question. So the question reads, which one of the following treatment is suggested for long bone segmental defects? So here, the long bone segmental defects refer to defects which are of length or size greater than 5 centimeters. These are the defects which will not heal on its own. If you guys ever had any fracture in your life, and maybe a minor fracture, recently it happened with my friend. So the doctor didn't give any like treatment, like he didn't prescribe any medicine except calcium. Okay, except calcium. Like it's like a simple supplement to the body. Apart from that, no medication was prescribed to him. So he had a fracture in his wrist, but it was a minor fracture. So, and only thing the doctor did, they put on a plaster so that you don't move your fractured side too much. So bone is a very like it can regenerate itself very fast. Okay, so if it gets broken in small size, it will regenerate itself, it will heal itself. You just have to take care of it properly. But if the bone defect is of larger size, like greater than 5 centimeter, then even the plaster won't work. You need some intervention, like you have to insert some kind of support inside the body that only a surgeon can do. So there are four options, A, B, and C. So which of the four options do you think is the is a good treatment option for treating this kind of long bone defect? The option one is cylindrical mesh technique, B is nanoparticle drug delivery, C is fixing stainless steel plates, and D is none of the above. Now imagine the bone defect is something like this. So I'm drawing very roughly, okay? Very roughly. Don't think of my drawing as the true representation of a bone. So I'm indicating that this is a bone defect, which is like say of 7 centimeters. Now doctor want to join these two bones together. So which of these four options would you suggest him? Have you understood the question? If yes, then go ahead. Don't worry if you are wrong. Just whatever seems right to you, you can answer.
C.
See, okay. Seems a viable answer. Anyone else would like to try?
See, ma'am.
See, okay. Anyone else? Anyone else have any other thoughts? Okay. So let me help you. Uh, by the way, the C option is not correct. All right. So let me help you a bit more by giving you a hint of how the stainless steel plates usually look like, which the doctors usually use. So they are like a plate, and there are some holes in it through which you can drill in the screws. And these screws are meant to like support. Okay, like so if this is a bone, the stainless steel plate will be screwed on to this particular bone segment. So this is a healthy bone that I drawn, but suppose this bone has like brittle creases in it. Okay. Now, there's another option. So option B is not correct. Okay. Let me help you with that. C is also not correct. The correct answer is A. Why A? So if you remember from the lectures, Professor Doble showed you guys of cylindrical meshes that looks like this, which again has holes in it. So in this treatment option, what people do is they fill this particular cylinder with some like allograft, maybe some pieces of bone that they take it from the patient only, or they can put in some hydroxyapatite and make a block, cylindrical block. Now, what the surgeon can do, they can take this particular block and fit it. Now, do you understand how a cylindrical plate, sorry, how a stainless steel plate and a cylindrical mesh, like how these two things are different and why cylindrical mesh can be used here or is more appropriate here? So, if in case of this cylindrical mesh, I think, sorry. So this is your bone and this is your defect area. Now you put a cylindrical plate like this. Okay, and maybe you can put another side. Now the defect is too large. All right, the defect is too large. The cells that are here, the cells that are here, how will they meet? There's a space. No, maybe you put two more. You put four plates to cover the entire area, a one at the back as well. Then also, how will they meet? You need some you need to provide some medium through which the cells of the bones they can migrate into, okay, and ultimately they meet and form the bone. So the cylindrical mesh is like a cage, all right, into which some biocompatible ceramic materials like hydroxyapatite or allograft is put inside and packed and put like and placed in between the two bone segments. Got it? Have you guys understood? Okay. So the correct answer is cylindrical mesh technique. Now, for uh, for the bone tissue engineering application, you suppose are thinking of choosing a biomaterial and use it as a scaffold that you can use for maybe repairing or regenerating bone. So, what properties should it have? First thing is the mechanical property of the material. The mechanical property should be similar to that of the native bone, be it is Young's modulus or compressive strength or yield stress, like whatever. So that values should match to the native bone. Otherwise, what will happen if the biomaterial is very the strength of the biomaterial is very high in comparison to the bone, then you will see the stress shielding happening. Another property should be the architecture of the scaffold. It should be very similar to the native bone. So the bones are very porous in nature. So you can create a scaffold which is again having porosity. Then you can mimic the native bone structure, like the defects, the bending wherever the native bone is there. You can mimic that, and in that way, you can design your scaffold. Then biodegradability. So the bones, if you're creating a bone scaffold using biodegradable material, suppose, then the rate at which the degradation is happening inside the body, it should match the rate of new bone formation. This is another criteria. Then it should be highly porous because, as I told you, bone is a very porous organ. So that thing has to be mimicked. And the pores should be interconnected in nature so that the cells, the fluid, the blood vessels, all the things they can form in a continuous manner. And the flow of nutrients and cells, it can happen continuously from one end to the other end. So there should be interconnectivity between the pores. And the porosity, desired porosity range is around 70 to 95%. And of course, the biomaterial should be biocompatible, meaning it should not cause any harm to the host. Then there are four terms that that is only used for bone tissue engineering applications. First is osteoinductivity. It means the ability of the biomaterial to promote stem cell differentiation. That is called osteoinductivity. Now, the biomaterial can itself promote this, or it can happen in presence of some growth factor. So the scaffold can be engineered in such a way that it sustainably release growth factors, and that in turn helps in stem cell differentiation. Then osteoconductivity. It means the biomaterial should be able to promote cellular attachment, migration, and proliferation. These are the basic processes that the cell has to undergo. Without, if the cell doesn't migrate, doesn't proliferate, doesn't adhere, then the further uh, things like regeneration, okay, repair, those things won't happen. So basics, the cell first adhere, then it should migrate to a new location, then it should increase in number and cover the area. So these things should happen. That is called osteoinductivity. Then the biomaterial should be also osteogenicity. Now, if the material is osteoconductive, means your cells are able to perform all its basic functions, then it can also proceed to form a new bone or a segment of bone. That is osteogenicity, that is promote the new bone formation. Now there are, in the bone there are various stem cells or progenitor cells. They can also undergo the basic cell processes like attachment, migration, proliferation, and in turn help in regeneration process. Then osteointegration, this is the last thing that you guys should know. It means then now this term osteointegration is not just important for tissue engineered uh, bone scaffolds, but it is also important for the implants like the stainless steel implant or titanium implants, because whatever implant that goes inside your body and a direct contact with the bone, they should communicate. Means there should not be any gap between the bone and the implant, and over the period of time the body should accept it kind of, and doesn't allow fibrosis or the formation of fibrous tissue to form between the or at the contact point of bone and the implant. The body should be able to accept it, okay, then only the intended application, that is bone healing, that would happen. So bone integration, you can say, is the first step or first property that one should look when they are trying to make a bone scaffold or a bone implant. Now, when you are thinking of working with metallic biomaterials, there are various challenges associated with it. Now, it is very much clear from this particular network diagram. So here, some common types of metallic biomaterials are mentioned, like stainless steel, chromium cobalt alloy, titanium alloy, nickel titanium alloys, okay, then porous nickel titanium alloys. So these are some metallic biomaterials or examples of metallic biomaterials. So people have observed the stainless steel. If we consider for stainless steel, it it is it doesn't have a very good corrosion resistance. Also, the elastic modulus is very high, and it is also prone to wearing. So because of these reasons, it can undergo a release of metallic ions, means metal ions will start leaching off the surface of stainless steel. Then it can also show the stress shielding effect, as well as in the body there can be debris, metallic debris floating inside. So that in turn can lead to reduction of the implant life inside the body. The implant will fail much earlier than intended. The implant will cause cytotoxic effects or toxicity inside the body, and over the period of time we can also see that the bone and the implant contact is has become loosened, so the implant can come out. Okay, so when these things happen or start to happen or start showing the symptoms that it's going to happen, then the person has to go to the surgeon and revise it or correct the problem that is happening, that is undergo a revision surgery. Okay, similarly, we can reason for chromium, cobalt alloy, titanium alloy. Okay, so you just have to follow the arrows and then you will understand because of this inherent property of this particular biomaterial, we are going to face this problem, and then ultimately the person has to undergo revision surgery, which is a very painful process again. So what people do then? If people don't want to revision surgery, what people do, they choose other ways to create better bone implants. How do they do that? They incorporate some porous coatings. So this will again help in osseointegration. Okay, this thing will also help in osseointegration. Then you can use, for porous coatings you can use ceramics, bioactive ceramics or metallic glasses. And people have saw or reported that these type of ceramics or metallic glasses, they help in osseointegration. Once osseointegration happens properly, then migration of cells like osteoconductivity, then osteoinductivity, so all these things will happen simultaneously or one after the other. And people have also thought of strategy of growing a bone tissue in vitro, like outside the body in lab, and then implanting it. That is the tissue engineering approach. Okay, so these approaches are thought or have been like researched thoroughly so that we can overcome the challenges of metallic biomaterials when they are used alone. Now, if we compare the physical properties of metals, ceramics, and polymers, then what we know from that. So, like, if you guys have any queries, like till slide number 8, if you guys have any queries, you can ask. Any queries? Have you guys understood everything? Or if you
Ma'am,
have
can you
query, yeah.
integration again?
Yes, can you repeat? Sorry, your voice broke in the middle.
Uh, am I audible? Hello.
Yes, yes, you are now audible.
Ma'am, can you explain osteointegration
So,
again?
os okay, okay. So, osseointegration means when your implant and the bone, so fracture site of the bone, when they come in direct contact, the body has to, or the bone cells at the particular point where there is bone cells and the surface of the implant, they should be like come into harmony. Means the cells from the fracture site should start attaching on the bone implant. The bone implant itself shouldn't start leaching out any iron so that it causes toxicity. Okay, so that particular interaction, if it happens favorably, then the implant properly integrates. Okay, so that particular phenomena is called osseointegration. If the if some problem happens, suppose metals start leaching out, and because of which inflammation response starts, okay, then the body will try to shield the particular area from the rest of the body by creating a fibrotic tissue around the bone implant. And then what will happen? Your bone implant will not be able to do its intended job. That is to promote healing, right? Promote healing of the bone cells so that they itself form a bone. So that purpose won't be solved. Instead, the implant, since it is a very a hard material, suppose the patient is not careful about the surgery site, then it can definitely come out. Okay, and will again risk the and again will have to again undergo a surgery to remove it. So if that is why also integration, it means this term has a much more deeper meaning. I tried my level best to explain it in a simple language. But okay, so in summary, what I tried to say is the body or the surface of the bone or the cells from the surface of the bone, they should able to accept the implant. They should not repel it, as well as the implant should be able to very nicely uh, what is it, fit into the bone site. So I hope some idea you must have gotten what is osseointegration.
Yes, ma'am. It is similar to that of, I mean, like the material is biocompatible and oxio integrated. So I mean, like it is different or same.
So biocompatibility again is a very big umbrella. Okay, so if all the osseointegration happens properly, osteoconductive happens, osseointegrative means if all these things happens, then you will be able to say the material is biocompatible.
Okay, okay. Yes, ma'am. Understood.
Yeah. Any other queries? Okay. So coming to a slightly different topic. So I'll now try to compare the physical properties of three classes of materials that we have seen so far: the ceramics, metals, and polymers. So in depth, we have seen only metals. In coming lectures, we will go into polymers and later on ceramics. So, if we compare the properties like hardness, elastic modulus, thermal expansion, ductility, corrosion resistance, resistance to wear, electrical conductivity, density, and thermal conductivity. If we like, these are some basic physical properties. Okay, and if we compare, then what we understand, what we then it will give a deeper understanding of what is a metal, what is a polymer, okay, what is a ceramic. So we will be able to better imagine how a ceramic will behave, how a metal will behave. That is why this discussion is important. Now, hardness. So we discussed what is hardness. If anyone would like to give it a try and explain to everyone what does he or she understand by the term hardness. So be prepared, okay? I'll ask each of these property meaning from you guys because we have already seen these terms somewhere along in the lectures. So I expect that you guys already know its meaning. If you don't know, simply Google it. You guys have your phone. And then what you understand from the Google, you tell me. Not read the statement. All right. Tell me what you understand. So what do you mean by hardness? Anyone? गूगल में पढ़ के बता दो, कोई दिक्कत नहीं है, लेकिन don't repeat that statement to me. You have to explain it in your own words. What do you mean by hardness? Okay. While you guys search for hardness, tell me what is elastic modulus? Or what does the value of elastic modulus helps you understand? You guys have been calculating elastic modulus, right?
where the material deforms to its original state. That's equal to strain.
Sorry, can you repeat again? Your voice got cracked in the beginning, so I didn't catch your complete answer.
Range where stress is directly proportional to strain and
Hmm.
deforms back to its original state.
Hmm. So that region is elastic region. That what you said now, that is Hooke's law basically. That is the elastic region. So from that region, you get the value of elastic modulus. But I'm asking like, what is physical significance of elastic modulus? Suppose like here it is written ceramic has a higher elastic modulus than metals, and then metal has a higher elastic modulus than polymers. So what does this mean?
Ceramic will not go to deformation like plastic deformation.
Okay, okay.
It will
Anyone?
only
Yeah. Like maybe frame it in another other words. Like think like you're very close. You're very close, but again I'm just looking for one word, just one word. If anyone would like to again
will
retype. Yes,
The stiffness of a material, how stiff the material.
yes, yes. You can use the term stiffness, you can use the word strength. Okay, it has a very high strength, you can say. So yes, that is what this statement means, this particular point means. Now, have you guys seen what is the meaning of hardness, or you guys need more time? Okay, take your time. Next point, I'll come to thermal expansion. So I hope you're able to understand what is thermal expansion. Yes, no. In presence of high temperature, the material will expand. Okay, that is thermal expansion. Then ductility, already I have explained that the material will be able to turn itself, or when applied some load, it can be, or when you apply some tension, it can deform into thin wires without fracture. That is ductility. Then corrosion resistance, I have already explained. It is the resistance to corrosion, means in presence of some harsh environment, the surface of the material will not come off, means ions from the material will not start leaching out. That is corrosion. Where again it's like rubbing. Wearing means some surface is rubbed very so many times, because of which the structure starts deforming, the surface starts deforming. So if it doesn't happen, if the material is resistant to this, that is called resistance to wear. Then electrical conductivity, it means whether it can able to uh, allow current to pass through it. That is electrical conductivity. Density. So what is the meaning of density? What do you understand by density? Don't tell me mass by volume. What does it really mean? Come on. What is the meaning of density? When someone tells you that this say metal is more dense than ceramic, what does that mean? Okay, I will not tell you. This is like something that you guys should find out. Okay, yeah,
Excuse me. The
yes.
density, is it a heaviness of a material, or how light or heavy is a material?
It is the mass, no,
Okay.
that is the mass. So we compare density. It is, no, no, I won't tell you.
Compactness.
Yes, yes,
Compactness.
compactness. Okay, very, very close actually. So, okay, since you guys gave a try, let me just give you, tell you what is density. So if you suppose have a cube, okay? Now just listen carefully. You have a cube. This cube say represent unit self of titanium. Now there is another cube. This is slightly larger, and this suppose represent stainless steel. Now this within this cube, it's a hollow cube and it is filled with some atoms. Here also filled with some atoms. Now the number of atoms in the first cube, which is smaller, is 100, and the number of cube in the so the number of atoms in the second cube is say 50. Now tell me which is more denser.
Titanium.
Titanium.
Yes. Now do you understand? Density helps us to compare between elements of different geometry. It is an inherent property of a material. So no matter if I had drawn a cube, maybe I could have chosen another geometry, maybe a cylinder. But how many atoms are packed? Okay, how closely they are packed. If in a small space you find so much of particles packed inside, that means it is densely packed. We call it densely packed. Okay, similarly, but in other case, air air is very uh, air is less denser than water. Now you understand. So that is the real meaning of density. So when I say that metals are more denser than ceramic, so the metal atoms within a block of a or within a plate of a metal, it's is more. Okay, in comparison to ceramic, if you create a similar geometry, you will find the particles within the geometry is lesser. It cannot pack that tightly. The particles are shaped in such a way. So that is what it means. Then thermal conductivity, again, the ability to pass heat through it. So if you compare all these properties of metals, ceramic, and polymers, then you will be able to imagine uh, what does metal can do or what a ceramic can do and how a polymer is different. Like you will be able to distinguish these three very clearly. Now, hardness, anyone found out? No? Okay. So hardness is a property of the material to resist any type of deforming force on it. So when it comes to ceramics have are much more or have a very high hardness in comparison to metals. And whereas if you see, I told you metals are ductile and malleable. Means what? We are easily transforming its shape to metal wires and plates or sheets, means it can it can like it doesn't have very high resistance to in a deforming force, whereas it is very difficult to shape a ceramic material. So so suppose you have a chalk, okay, you have a chalk, and you want to carve it, okay, you want to carve it. Now tell me, and carve it maybe into a cone, will it be easy or difficult? Will you get perfectly shaped cone from a cylindrical chalk size? No, right? Or yes? What do you think? You have a cylindrical chalk in hand with you, and you are trying to carve a cone. Will it be easy or difficult? Yes, no, anything? So it's very difficult actually to make ceramics of different shapes. Okay, you cannot get a very polished surface from a ceramic like block, like hydroxyapatite or chalk, right? So these are very difficult. You have to use much more advanced techniques to get shapes of desired for a desired application. Then elastic modulus, as I told you, the elastic modulus for ceramics is very high. Metals, they can easily allow the heat to pass through it, okay, and expand. Whereas polymer also, it can increase its volume, and ultimately if the temperature increases beyond its transition temperature, it can start melting and transform into liquid. Then ductility, yes, metals are very highly ductile. Ceramics are not that ductile. And then corrosion, when it comes to corrosion resistance, ceramics can provide very good corrosion resistance, which is why, as I told you in the previous slide, people do some ceramic coating over metal implants in order to overcome the limitation of metals. Similarly, it has a very good resistance to wearing. And metals, like it can conduct heat, it can also conduct electrons and pass current because of its structure, as I already explained. When it comes to density, metals are much more denser than your ceramic and then your polymers. So I hope you have understood it. If not, I request you to do some research on your own. Okay, go through some good, well written, simple articles, maybe that will help you understand the meaning of each of these physical properties. Then you will be able to better imagine how a metal works, or a ceramic work, or a polymer work. In this here, I'm actually showing the stress and strain diagram of metal, ceramic, and polymers. Here, ceramic, if you see the curve for ceramic, the elastic region where the stress is proportional to strain, this particular region. If you observe this region slope, that is your elastic modulus. That is much higher in comparison to this ceramic metal, and here the elastic region is only up till here, and the slope is this. Now if we compare the slopes, then it is evident that ceramics are having a very high elastic modulus. It is much more stiff. And when you compare the plastic regions, so the region which is not linear anymore, that is your plastic region. Ceramics have a very short plastic region. They will easily fracture, all right, and break. Whereas uh, if you see for metals, they can still deform without a breaking. That is why they are ductile or malleable. Whereas for polymers, this plastic region extends very long. So if you compare ceramics, metals, polymers, in lab, it is very easy to work with polymers because polymers, they can change its shape, or you can work with polymers even at low temperature and make your structures at room temperature. That is why polymers are like very, very hot topic, and it is like very easy to work. Whereas for metals, you need special conditions to process, all right. And for ceramics as well, you see need some special training. Now coming to another different topic. So the last topics, the previous topics that we saw, anyone else has any doubt on that? Almost everything is clear. I'm not asking everything is clear, almost. Yes, you have a query, then go ahead. Someone raised their hand and then lowered it. Okay. You if you can maybe give me a yes or no by unmuting yourself. It's clear. Or you can maybe gives a thumbs up by giving a react. I don't know how it works, but people have been doing it. If not, I can definitely go back. It's not necessary for me to complete everything in one day. I'll continue in the next week, but the topic should be clear. If you have any speck of doubt in your mind, you should ask. Hello, am I audible?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, yes. The previous topics are clear? Is there any doubt?
Yes, ma'am.
Okay,
No.
no doubt. Okay. So, coming to this new topic, here we'll briefly discuss about lattice structure of a crystal. So, the smallest unit of a crystal is called a unit cell. A unit cell itself repeats, when it is repeated infinite number of times, it will form a crystal structure. And a unit cell is defined by three axes. I hope you guys have already seen this diagram in my previous discussion sessions. So the three axes are named as A, B, and C. A is along the x-axis, B is somewhat along y-axis, and C is along z-axis. So these are the three axes of a unit cell, and it is a unit cell also has some angles or interaxial angles, which are alpha, beta, and gamma. Alpha is present between B and C axis, gamma is present between A and B axis, and beta is present between A and C axis. This is how, so when we define the values of A, B, and C, and alpha, beta, gamma, we get different types of unit cells. So there can be various types. So we can see this particular diagram. So there is cubic type, cubic, tetragonal unit cells, monoclinic, orthorhombic, then rhombohedral, hexagonal, triclinic. So these are all classes of unit cells. So there are 7, and each at least have and when we see how many types of unit cell is present within one plane, we can count it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and there are total 14 types of unit cells. Cubic has 3 types: simple, where the atoms are present in the corners; body centered, with one atom, additional atom is present at the center of the body. So 8 plus 1, 9 atoms are there. And the face centered. Here, apart from the atoms at the corners, there are also atoms present at the center of the each face. So there are 6 faces, right? So there are 6 atoms, 6 plus 8, there will be 14 atoms. So in this way, the atoms are distributed within a cubic type of unit cell. And they're named like that, like simple cubic, body centered cubic, BCC, face centered cubic, FCC. Similarly, there is heterogonal. So there is simple heterogonal, body-centered heterogonal. Okay. Then monoclinic, there is simple monoclinic where the atoms are present at the corners. Then end-centered monoclinic. Here the atoms are present at the center of the face, at the top, at the bottom face. Okay. So there are only 2 additional atoms, 8 plus 2. Okay. 10 atoms are there. Then when we come to orthorhombic, there is again simple orthorhombic, and there is body centered, face centered, and end centered. End centered means at the faces, the bottom face, the bottommost face, and the topmost face will have one atom at its center, that is end centered. Rhombohedral, only one type. Okay, that is simple one, simple rhombohedral. Hexagonal, again only one type. Here the hexagonal faces, which is making the hexagonal faces are are present at the bottom and at the top, and in the hexagonal faces or the center of the hexagonal faces, you will find one atom, that is hexagonal. Okay, and there is triclinic. So these are 14 types of unit cells that people have defined. And when one type of unit cell repeats itself infinite number of times, it creates a crystal lattice. Now, what is Miller index? So Miller index, it helps or it describes the orientation of a plane in 3D lattice with respect to the axes that we just saw, A, B, C. So a unit cell will have axes A, B, and C. With respect to that, there will be some planes, but how the plane is oriented. So that description is given by Miller index. The value of Miller index will be always in integer form. It can never be fractional. Then the notation. When it comes to notation, how you represent Miller index. So HKL are integer values, suppose, are which are in X, Y, and Z direction. Okay. So when we write H, comma K, comma L enclosed within round round brackets, that represents a point. So in a plane, XYZ plane, that is a Cartesian plane, when you ask to plot, say, where is 1, uh, 3, and 5, you can like plot like this with a point. That is your notation for a point. Where the notation for a plane, please note there are no commas. So when you are asked to give the Miller index for a plane, you always have to remove the commas, but it has to be enclosed in round brackets like this. Then for a vector, to represent the direction of a vector, you use a notation like this, where there will be square brackets. And when you have to represent the family of planes, not one plane, multiple planes, then you use curly braces. So note, only the point notation will have commas in between, whereas notation for plane, direction, and family of planes, there will be no commas. Only the type of bracket that you use is different. Also, in your notation, you will not mention negative sign. Means -2 will not be written like this. Rather, -2 will be written with the bar symbol on top of it. This will denote -2. Okay. These are some basics about how to represent Miller index and what mistakes not to do when you're representing the Miller index. Now, assuming that you have understood how to uh, like determine the Miller index of a plane, based on that, I'll do some examples. But if you have not understood, don't worry. Maybe these examples will able to help you. Plus, but please let me know if you have any queries. Okay, then I can describe it, or I can try to describe it in much more detail. So in this example, you are asked to sketch the correct plane that that is represented by this Miller index. So you are given the Miller index, and for that Miller index, you have to draw the plane. Now, this is your unit cell, and these are your axes, or I have represented with vectors: A vector, B vector, and C vector. Okay, for a unit cell. But this is in X direction, this is in Y direction, this is in Z direction. Now you're given the Miller index. You have to find the intersection points or intercepts. You have to find the intercepts. How will you find? You will take the reciprocal of these values. That is 1, 1/2, 1/4. Now 1 is in the X direction, so it will be the point of intersection will be this. Okay, A. Okay, then half, it is in the Y direction. Now if this is 4 Armstrong, okay, the half will be somewhere here, B/2, and Z is in, so 1/4 is in Z direction, that is 1/4 of this 8 Armstrong. This is the values of A and B, and we always represent the planes with respect to the axes of unit cell A, B, and C. That is why I'm using the values A, B, and C to find the intersect points. So it is 1/4. So it will, like, approximately it will come here. Okay, not half, less than half of half. So C/4. And when we draw lines to connect these 3 points, you get a plane. This is your plane. So this is how you will be able to find the plane or position of the plane or the orientation of the plane when the Miller index value is given to you. Have you guys understood? We'll do one more example. Then now in that example, you will answer where the intersect point will be. But just let me know if you have understood this particular example or not. Okay, I got one thumbs up. Anyone else would like to indicate that they have understood? Okay, 2 thumbs up. So rest of you, if you have any doubt, let me know. This is a very important topic for this week. and it will definitely help you in solving your assignment problem. Okay, I'm assuming that all 8 of you have understood. Now let's move to a similar problem. Now here your Miller index given is 0, 1, 2. Now you have to sketch the plane that represents this Miller index. So what is the first step that I should do? You guys direct me. What's the first step?
Reciprocal.
Yes, yes. So you have to first find the intercepts, and for that you have to take the reciprocal values. So 0, if you take the reciprocal of 0, it will come to infinity. Then 1 will remain 1, and this will become half. So these are your intercepts value in x, y, z direction or in a, b, c axes. Now infinity, when you get infinity value, it means it is parallel. This plane is parallel to here infinity value you got for x. So it is this plane is parallel to x axis. Okay, this is your x axis. You won't find any intersect point on the x axis. Okay, now b. B is 1 along the b axis. The intercept is 1. So this will be your point. Let me use black. This is your b. And along the z axis, the intercept is half of c. So c by 2. Now you got two intersection point. Now how will you draw the plane? So you know the plane is parallel to x-axis. So this is parallel to x-axis. This is parallel to x-axis, and this is how your plane would look like. So this plane is meeting only your y-axis and z-axis, whereas this and it is parallel to x-axis. This is how your plane would look like. Understood? Any doubt? If there is any doubt, let me know. I hope there is no doubt. Okay, I got one thumbs up. Okay. So I expect, I'm assuming that you guys have understood. Now this is another example problem. Here, what is asked is you have to find the Miller index. The plane is given, but you have to find the Miller index. So the intersect points are, what's the intersect points? What are the intersect points? Along a x-axis, there is a by 2. Then it is intersecting at b by 2. And here it is c by 2. Then take reciprocal of this. You will get 2 by 2 maybe. Here a value is 4. So you will get 2. Here I should actually let us let me clear the pen marking. Here intersects, I should write like this, not A by 2, 1 by 2, 1 by 2, and 1 by 2. And when we take the reciprocal, we'll find the Miller index. So Miller index will become 2, 2, 2. Okay. Here, why here actually A, B, and C, like with respect to A, B, and C, that is why it is written like that. But the intersect point is half, half, half. Okay. Understood? Okay. Coming to the next, again, a very similar problem. Okay, this is the plane given to you. You have to find the Miller index. First, find the intersects where this plane is intersecting. At x-axis, it is intersecting at 1. This is the A value, it is intersecting at 1. Then if you see, it is not intersecting anywhere. It is not intersecting anywhere at y-axis. So it is parallel. So we take infinity. And if you see, it is intersecting at 1 along the z-axis. Take reciprocal and you will get the Miller index. What will be the Miller index? 1, 0, 1. Okay, understood? Okay. Now this is a question. A very similar question to this is given to your assignment as well. So you, in this question, it is made very simple. You don't have to imagine where the plane or how the plane would look like. You are directly given that the plane cuts the x, y, and z axis at these points. So you are given with, so you have the intercepts with you. Intercepts are -4, 8, -4. And you have to find the Miller index. So what you will do? You will take its reciprocal first. It will come out to -1 by 4, 1 by 8, 1 by 4. Now tell me quickly, can the Miller index be a fraction? Yes, no,
No.
no. So we have to make it into whole integers. So it cannot be in fraction form, it has to be in integer form. So what we can do? We can multiply all the three values with 8. Okay, multiply by 8, you'll get 2 bar, 1, 2 bar. So this is what the answer should be. Then see the options. Do you get a similar one? Yes. Option number D is your 2 bar, 1, 2 bar. Got it? This is how you will calculate, or this is how you should calculate. Understood? Okay. So could you have multiplied it, multiplied this intercepts or the reciprocals with 4? No, right? You will again get a fraction. So you have to choose a value in such a way that you don't end up with a fraction, rather you should get integers. Now, so this is like, okay. So you can try yourself of how to draw that particular plane that we just obtained, this intercepts, and you can try maybe. So that is for you. Now, this is in this question, you are given the values of the three axes and the corresponding angles. And by looking at these values, you have to identify which crystal system it is. So first, you have to know how do the people define the crystal system. So if you look at simple structures where the atoms are present only at the corners, we are not talking about face centered or body centered. You just look at that, look at this particular diagram. Here only the simple structures are given. There you will see the values of A, B, C, alpha, beta, gamma. That is given, kind of like the for symbol cubic, A, B, and C, they all will be equal, or they will all have equal values, whereas alpha, beta, gamma, they'll be of 90 degree. So if these two criteria is fulfilled, then the unit cell is of simple cubic nature. Similarly, you can define like that for all the 6 types of crystal system. Now you see the values. A is 1.2, B is 2.3, C is 3.3. Now first question, are these three values equal? Answer is no, they are not equal. We get a relationship which is like this. A is not equal to B, B is not equal to C. Then go back. So in this particular diagram, you see this relationship for orthorhombic, monoclinic, triclinic. That's it. Only these three types have a relationship where all the three axis values are not equal. Now you look at the angles. So alpha is 80 degree, beta is 95 degree, and gamma is 85 degree. Now are these three are like, what can you say? Like they are not equal, right? That doesn't seem equal. Neither of them are 90 degree, correct? So we get a relationship which is like this. Alpha is not equal to B, beta is not equal to C. And when you go back and compare and look into the three options, what you see? The orthorhombic will definitely disqualify because orthorhombic desires that all the three angles should 90 degree. Monoclinic will also disqualify because the alpha and beta should be 90 degree, whereas gamma can be anything other than 90 degree. Whereas the triclinic, you see, it is not compulsory for a triclinic unit cell to have alpha, beta, and gamma of 90 degree angles. Now you compare. So your unit cell is triclinic. You come back to the options, what you see? Option number D is correct here. The structure is neither monoclinic, neither hexagonal, neither orthorhombic. Okay, this is how you should approach a problem that is like this. Understood? Okay. I'm assuming that you guys have understood, but lazy to say yes or no. Okay. There's another question. So in this question, you are asked to determine the fractional decrease in atomic packing factor. So atomic packing factor basically helps you understand that within a unit cell, uh, how the atoms are packed. Are there any void spaces? So that this type of question, it helps you understand. So higher the atomic factor, higher will be the number of atoms and less the void space will be. Okay. So you have to determine the decrease in atomic packing factor, or in short APF, of iron when it is cooled from 1000 to 900 degrees Celsius. Simple. Now it is given to you that iron has a unit cell of BCC type at a lower temperature, whereas FCC unit cell is there at a higher temperature. Now the iron is cooled. Initially it was at 1000 degrees Celsius, correct? Now tell me, what is the unit cell type here for 1000 degree, whether it is FCC or BCC?
FCC.
Yes. The unit cell type is of FCC. Now, if you go to literature or even search internet and like search the atomic packing factor of FCC. You can calculate as well, by the way, on your own. It is very simple calculation. It is taught in high school. So the value is 0.74. What this means? It means 74% of unit cell comprises of atoms. That is what this means. And rest is white space. Whereas when it is cooled, it becomes 900 degrees Celsius, and then the iron transforms its crystal structure to contain BCC type of unit cell, and for that, that atomic packing factor is 0.68. Now you have to just calculate the percentage decrease. Simple, right? So initially it was 100 degrees Celsius. So initially that atomic packing factor you have to consider for FCC. Then finally what you got? You got a BCC structure, and you have to find the difference between these two values. Now take a modulus of it so that you get a positive number. Okay, take a modulus because you will get an so percentage cannot be negative. So yeah, when you put in the values, so I forgot to incorporate percent, means you have to multiply with 100. So tell me what value are you getting? At the beginning of the class, I asked you guys to get a calculator. So now is the right time to use it. Tell me what's the value you are getting.
Minus 8.10.
Actually, if when you have put the modulus, no, the minus sign will disappear. Okay, it will become positive. So
Okay.
8.110, no, so 8.1 we can take. So is everyone else is also getting this 8.1? Okay. So let's see if we are correct. Yes, the answer is 8.1. Okay. So in this way, you can calculate the other way around. When the iron is heated, okay, then you can also calculate the percentage increase in atomic packing factor. What this value tells you? It tells you that 8.1% less atoms will now fit in because the structure has become BCC, body centered. Means the atoms will in a unit cell, less atoms now are present. How much less? 8.1%. Now this is a question. Uh, Graphite has a lower coordination number than diamond because, so graphite and diamond, these are like form of carbon only, but the arrangement of carbon is very different. In graphite, one carbon atom is surrounded by three carbon atoms. It has a coordination that makes the coordination number of 3. Whereas a diamond, it one carbon atom is surrounded by uh, right 4 carbon atoms. So for diamond, the coordination number is 4. Okay. So that is why the statement that the graphite has a lower coordination number than diamond because. So now if you look at the structure, of graphite and diamond. So graphite is, what do you say, a sheet kind of structures are present, whereas diamond, it's much more denser, it's much more bulkier. Okay, so the correct answer for this question is A. Graphite, because the graphite has a 2D layer, it can like form sheets like one, and they form a layer, one sheet on top of the other. Because of that, it has a lower coordination number. Whereas for diamond, the coordination number is higher. It has a tetragon kind of structure. Whereas other two options are not relevant in this case. This question is just for your general knowledge. That's it. Now, is another question. Calculate the number of cobalt ions released as M into 10 raised to power n. So basically, these are the variables m and n you have to calculate. See, you have to calculate m and n. So calculate the number of cobalt ions released in a year from the head that is of 14 dia of a hip joint prosthesis. So this is a hip joint prosthesis. This is how a hip joint prosthesis looks like. And this is your head. And this is your head. So it is a sphere kind of a shape. Now this particular head is made up of an alloy that contains 45% cobalt. The wear rate, so due to motion, due to rotational motion, it will start wearing out. So what is the rate? Rate is the diameter of the head will decrease at around 0.1 mm per year. Every year, the diameter will become shorter and shorter because of wear. So this is its wear rate. And all the atoms become ionized. As it is wearing, ions start releasing. Okay, which is why you have to calculate the number of ions released in a year. What is the much any like on what more given is what more data is given to you? Density of cobalt is given and the atomic weight is given. You have to calculate the number of ions, cobalt ions released in a year. So how will you start? You will first mention in your notebook what all data is given to you so that everything looks simplified. First, you know the diameter of head. It is 14 mm. And radius, similarly, what will be the radius? 7 mm. We can convert it into centimeters as well. Then in that case, it will become this. And also you are given uh, that alloy contains 45% of cobalt. So atomic percentage of cobalt in the head is what? It is around 45%. Then the wear rate is given. It is 0.11 mm per year or 0.011 centimeter per year. And you know the density of cobalt. 8.83 gram per centimeter cube, mass by volume. And the atomic weight is also given of cobalt. It is 58.93 gram per mole. Now you will first have to determine what is the surface area. Should rather so surface area. surface area of head. So the geometry of head is a sphere, and the surface area of a sphere we calculate using the formula 4 pi r square. So put in the value of radius. The radius is 0.7 square. So you will get the value in centimeter square. Okay, don't calculate it now. We will do the calculation together at the end when we have the final expression. So keep it like this. Now you know the linearly the how much varying is happening. That is in the radial direction, you know the wear rate. Now I want to know what is the volumetric wear rate. So for that, you will use the given wear rate. It was at unit centimeter per year into the surface area, which is in centimeters square. Now feed in the values 0.011 centimeter per year into 4 pi into 0.7 square centimeter cube per year. This is your volumetric wear rate. Like in a year, this much volume is lost due to wearing. Now you have this. Now you have to calculate what is the uh, number of ions. No. So you have to calculate what will be the number of ions. So number of cobalt ions released. Number of cobalt ions released per year. We are given the time frame of per year. So for that, you will the we have to construct the equation for us. So for that, use the why volume we are considering, because the entire uh, head will start leaching. So we have to consider the bulk as well, not just the surface. That is why I took or I calculated the volumetric wear rate. So first take that volumetric wear rate. Unit is centimeter cube divided by area. Then how much of the volume contains cobalt? That is your fraction of cobalt ions. Then the density, what is the density of cobalt? Rho. Rho is given in gram per centimeter cube. Then this is we have to calculate, ultimately we have to calculate the number of ions. So we'll take the help of Avogadro's number represented with Na. And you know Avogadro's number unit is atoms per mole, or in this case ions. Like this much ions is present in 1 mole. So we'll take help of that. And when we divide, then we will divide it with atomic weight of cobalt. The unit is gram per mole. So if we compare the units, so let me write it bit nicely. Ions per mole. Now see, if we compare the units, this mole gets cancelled, gram gets cancelled, centimeter cube is fine. The final, so we want to find the number of ions released per year. We didn't fit in the values just yet. We are just trying to see whether the formula that we have, whether the equation that we have constructed is going to give us the correct value or not. So for that, we just have to compare the units. So on comparing or cancelling out the common ones, we got ions per year. This is the value. The value that you will get will be in the unit of ions per year. So that is what you want, right? You want to know how much ions are released per year. So see yourself, this mole in the denominator and this mole, it gets cancelled. Gram gets cancelled. And here centimeter cube and the centimeter cube gets cancelled. You're left with ions per year. This Y is year. Now feed in the values. So volumetric wear rate is 0.011 into 4 pi into 0.7 square. Fraction of cobalt, how much cobalt ions are there, or cobalt atoms are there. You know from the percentage, atomic percentage, this one, you know from here. And that is 0.45. Density, you know, density is 8.83. Then what is the value of Avogadro's number? It is 6.022 10 to the power 23. Divide the whole numerator with the atomic weight. Atomic weight is 58.93. 58.93. Someone calculate this and let me know the value. Are you guys doing it? Have you solved it? Just use a
0.
calculator. Yes, tell me.
0.02.
0.
7 into
Only 1% tell me. 0.0. Again, repeat.
27.
0.027. Anyone else getting any other answer?
10 power 20 into 10 power 23.
Okay. Anyone else getting any other answer? This is the expression. Do it on your own. Don't worry. Whatever value he has got, I didn't say that is correct. So try it.
0.027
0.027.
into 10 power 23.
Okay. So you guys got this answer. So let me see if it is correct. It's not. The answer is not correct. So we have missed one thing, you know. We didn't consider that the entire, so if you see this particular diagram, this is the head, right? This is the head that for which we are calculating the release of cobalt ions. So if you see, the complete head is not or will not undergo tear. Only a half of it. A half of it the will be in direct contact with the hip. Only, so this is the socket into which this particular spherical head will connect. So only half of it will be in direct contact. So the release of cobalt ions will happen from only half of the volume, not the complete volume. So to take that into account, we have to multiply half here, and then we have to get the volumetric wear rate. So when we do this, when we multiply half here and as well as in this numerator, now tell me what you get. Is this you should get answer which is similar to this or same as this? Now tell me. So this is your new equation is this, where in the numerator half I've multiplied. What value are you getting?
Yes, ma'am. Same. 0.013 10 power 23.
Yes. So you should get. So if you take like write it in, what do you say, multiply with 100 and divide by 100, then you should get 1.37 to 10 to the power 21. So you got 0.0137 and 10 to the power 23, right? So you just multiply with 100 and divide by 100 in this side. So you will get this. So this is your answer. You have to calculate or get the values of m and n, right? So m will be 1.37 or n will be 21. So that's the answer for this question, or this is how you will solve for this type of a question. Okay. Now, few very basic questions about polymers. You already know what are polymers, like in the previous classes as well. You have seen some examples. So, polyvinyl alcohol. So, the short form for this is polyvinyl alcohol. What it is? Is it a natural polymer, synthetic polymer, elastomer, or thermoset? Anyone would like to give it a try? Okay, it's a synthetic polymer. It's not a natural polymer because it is not derived from a animal or a plant origin, means it does not come from nature, or we make it in lab. So that is why it is synthetic. Elastomer means something else. Okay, uh, like we add some additives to a polymer to make it much more um, like deformable. Okay, so I actually don't understand completely what are elastomer, but it is the correct answer is synthetic here anyway. Thermoset are those polymers which once in liquid state, and when you uh, mold pour it into a mold and you cast it into a desired shape, then after casting it is very difficult for us to convert it into a liquid. Those are called thermoset polymers, or thermosetting process is called thermosetting. So most of the polymers that people use to make plastic chairs or anything, say plastic chairs, in my mind I got that example. So you cannot really melt that again. If you even successful in melting it, you again cannot solidify it and get the same structure at the molecular level. There's another class of polymer called thermoplastic, thermosetting and thermoplastic. With thermoplastics, you can reheat it and convert it into liquid as many number of times. And once it converts to liquid, it will transform into a solid structure. That is called thermoplastics. Okay, so these are again another classification of polymers. So polyvinyl alcohol is a synthetic type of polymer. Now, which polymer will have oxygen present in it? So we have seen this type of question previously as well. For this, you have to first refer to the monomer units, how the monomer look like for each type of polymers. So there were the options that were given to us were polypropylene, PVC, PET, and PTFE. So although you know the answer is PET, so why PET is the answer? So for that you have to look at the structures. So polypropylene, as the name suggests, uh, propylene or propylene. Okay, this propylene means one carbon is bonded to three. So one carbon is bonded to two more carbons. So this particular unit is basically one N. This is N here. This is a monomer of polypropylene. So all are carbon and hydrogen only, no oxygen present. When you see at polyvinyl alcohol, polyvinyl chloride or PVC, there is a chloride atom present. Okay, no oxygen atom present. Whereas PET, the full form is polyethylene polyethylene terephthalate, PET. So PET is used to make plastic bottles, the bottles that you daily use to drink water. So those are called PET bottles. Often people call it PET, but the correct way of saying is PET or polyethylene terephthalate. So if you look at the monomer of this polymer, you will see the oxygens are present. Oxygen atoms are present, and there is also a aromatic ring present. Whereas PTFE, or it is also the commercial name is Teflon. Teflon coating you will find on various non-stick pans, okay, that you use for cooking food. So this PTFE, it stands for polytetrafluoroethylene. Here, there are fluorine atoms present. Okay, so actually here also fluorine atoms. Two carbon bonded to four fluorine atoms. That is why tetra. So this is actually a wrong structure. Should look like this. This is the correct structure. Understood? So I hope it is clear now. Right. Great. Now the last question for today's session. Um, you're given a polymer, this polyethylene, PE, polyethylene. So when we will discuss polymers in detail, no, during those lectures, you will better able to memorize the names of the polymers. Actually, you should, that is part of the learning of this course. You should remember the names of at least few common polymers, at least the ones which are heavily used for biomedical application. So next time when you come across, you will recall that, acha, this is the purpose of this polymer, this is the purpose of that polymer, this is this property. So you'll better be able to relate. So P stands for polyethylene. It is given that the molecular weight of P is 4.9 10 to the power 5 gram per mole. And the repeating, and it has a repeating unit of CH2. You just have to calculate how many repeating units will be there. So it's very simple. So first we have to calculate the molecular weight of this repeating unit. So you know, for carbon the atomic weight is 12, for hydrogen it is 1, then 2. So molecular weight of CH2 is 14 gram per mole. And this is the molecular weight of the entire polymer. So you know polymer is nothing but a monomer that are repeated n number of times. So you have to calculate the value of n here. That's it. So what you will do, you will, the number of repeating units, for calculate the number of repeating units, what you will do, you will simply divide 4.9 to 10 to the power 5 gram per mole will be divided by the molecular weight of the repeating unit, is 14 gram per mole. Someone calculate and let me know the value. Are you guys doing it?
0.35.
0.35, ma'am.
0.35. Try again. There is a 10 to the power 5 is there. The numerator is very large.
0.03 into 10 raised to 5.
0.035 into 10 to the power 5. Okay. So what we'll do? We will 135. It will come 3, 4, 5.
No, ma'am, 0.35 into 10 raised to 5.
Okay. Zero 0.35 to 10 to the power 5. So if we do it like this, there will be 30. This is the number of repeating units. So let's see if this is correct. Yes, this is correct. Okay, 35,000 repeating units will be there. So in this way, you can determine the repeating units, the number of repeating units when you have the molecular weight of the entire polymer, as well as the and as well as what is a repeating unit, and from that you can from the atomic weights you can calculate the molecular weight of one repeating unit. Okay, so this is it from my side. Like, this is all the topics that I had in mind to discuss with you guys. If you have anything else or any doubt regarding anything that we have discussed today, or you couldn't understand something in the lectures, let me know. I'll try my best to answer. Otherwise, I'll address it during our next session. Anything, or if anything other than the course content, if you guys want to discuss something else, also that's also fine. So these lectures, notes, and recording, everything will be made available to you. So you guys can go ahead and watch it in your free time. If there are any queries as well, you guys can share it with me. I'll try my best to answer it.
Ma'am,
Yes.
in one assignment question it states the angles and the lengths are differs, ma'am, but doesn't match with the cubic or any of the crystal system, ma'am. The
Okay.
question
Assign
was what is
week 6. No.
yes, ma'am.
See, I cannot give you the answer because the assignment is still not um evaluated. But let me have a look at the question. Oh. Again, so if can you see my screen? I have shown the slide where I discussed a similar problem. Now, don't
Yes.
answer, don't answer. Okay, but once you see this slide, you will be able to understand what is the correct answer to this question. Got it? Got the answer? Don't tell anyone yet. The assignment is still ongoing. Match the values of A, B, C, and alpha, beta, gamma with the types of unit cells. It is there on your screen, and then you'll be able to get the correct answer, just like we did for the example. Okay. Any other queries? Okay. If there are no more queries, are there any queries? Have you guys understood the topics that I've discussed?
Yes, ma'am.
Yes. Great. So I hope now you will be able to solve this week's assignment. Okay. And if they again, don't worry if there any problem in the question or not. Try to understand the question first. Think what is correct to you. Okay. If suppose there is some mistake or then reevaluation, everything will be done by the NPTEL. But your basics should be strong, your concepts should be correct. Then you'll be able to, find the correct answer. All right. So now I'm here to help you to understand whether what you are understanding is correct or not. So if you have any queries, you can ask me. We can meet again. We'll meet again next week on Saturday. Okay, there also we'll discuss. And at the end, like right before the exam, we will have a revision session as well of 1 hour. There also you can come with your queries on any topic that is discussed throughout this course. And also you can post your queries in the discussion forum. Whenever I get time or I'll get time, I'll look into it and try to answer it there. I'll discuss it in our session. So that's it then. It was nice seeing you all again this week. Many of you are repeating. That's good. Um, I hope you will also come in the next week. And I expect much more participation from you all. It becomes very boring to only speak. I also want to rest and ask, like, hear you speak. So next time, I hope you guys will be more free to discuss your doubts and more free to answer maybe. And okay, thanks for the thumbs up. So I'll see you guys in next Saturday. The recording, everything will be available. Okay,
Okay, ma'am. Thank you.
yeah, you guys can leave the meeting now.